This is an overview of injection, stimulation, and circulation activities at the Utah Forge site. As you can imagine, after drilling a certain number of injectors and producers, those wells need to be interconnected by hydraulic fractures. And this sort of describes those activities at the Utah Forge site. To put this into perspective, up to the present time at the Utah Forge site, 10 wells have been drilled. 3 of those are shallow permanent seismic monitoring wells. This is also accompanied by a surface network when stimulation is in progress. There's 1 shallow water well that supplies the water for the hydraulic fracturing. And then in addition to this, there are 4 deep vertical monitoring wells that are used for seismic evaluation during stimulation and during circulation. Finally, there are 2 highly deviated wells. They're deviated at 65 degrees to the vertical, and they're aligned in the minimum principal stress direction to favor orthogonal growth of closely spaced hydraulic fractures. So to date at the Forge site, there have been 2 stimulation campaigns. They've been designed to create hydraulically generated fractures and to interconnect production and injection wells at the site. The chronology of the stimulation is as followed, and this also includes the chronology of drilling the injector and the producer. So the injection well was drilled in the winter of 2020 and early into 2021. This was followed in April 2022 by 3 relatively small hydraulic fracturing stages created at the toe of the injection well. And the purpose of these was to site the production well, to see the extent of the fracturing, to assess difficulties that might occur when a larger fracturing campaign was initiated sometime in the future. In June of 2023, the production well was drilled and completed. And subsequent to that, in April 2024, 8 fracturing stages were carried out on the injection well, and 4 stages were carried out on the production well. Finally, in August of 2024, a 30-day circulation program was undertaken to assess the interconnectivity between the wells. To put this into perspective, and most of you will be familiar with this, this is a classic EGS representation which we've adopted at Forge. And you can see on the right-hand side some drilling trajectories of the injection well shown in red and the production well shown in blue. Now, in this panel on the right-hand side, the left-hand part of that panel shows an elevation view, and the measured depth to the toe, the total measured depth of the production well is just under 11,000 feet. You can look at the plan view on the right-hand side of that panel, and you can see that these wells were nominally drilled one above the other, about 100 meters between the injection well and the production well in terms of vertical separation. So the premise is, and it's been adopted here, to drill the injection well, and we'll refer to that as 16A 7832, or we'll abbreviate it just as 16A. Subsequently to that, 3 small hydraulic fractures were carried out at the toe of the 16A well. And the purpose of those was using microseismic monitoring to make an assessment of the morphology of those fractures and how much vertical growth was anticipated, whether there were any untoward issues related to the stimulation program. And indeed, it was found that those fractures grew maybe 400 feet vertical. And so that allowed us to site that production well 300 feet, 100 meters above the injection well. So with that preliminary siting done, this well was drilled, and it was drilled with the purpose of intersecting the microseismic cloud from those 3 small fractures. Subsequent to that, we have populated the lower half of both wells with hydraulic fracturing stages. It doesn't show up here, but we've explicitly stimulated both wells during this item 4 activities. So let's sort of look at some of these hydraulic fractures in a little more detail. We have an injection well drilled, and in April 2022, 3 small fracs were drilled at the toe of this well. And so you can see that the injection well is shown by the yellow arrow, and the dashed line is the horizontal projection of the lateral extent of that particular well. It was drilled at 65 degrees to the vertical, just south of east, in the direction of the minimum principal stress. Now, 2 of the stages on this well adopted standard hydraulic fracturing procedures for geothermal wells, and in fact those were adopted from the Fenton Hill stimulation in 1983, or they were at least identical or similar to that. They were slick water. They were done at rates between 35 and 50 barrels per minute. Large volumes were injected, and at Fenton Hill just under 6 million gallons was injected. And in one of the stages on the Forge project, small fluid loss material, micropropant was injected. Although we really won't talk about it too much because I don't think it had too much of an effect. So the aspirations of this initial fracturing were to assess the hydraulic fracturing height that would be achieved, because we wanted to grow fractures that were high enough that we could drill the production well into them. And it was seen that the growth was more than 300 feet. Now, of course, this is a microseismic cloud, and that enfranches the fracture, but it doesn't guarantee that the fracture goes to the extreme edges of the cloud. We were less concerned about the lateral length at this time. At some time in the future, lateral length could be a substantial consideration, because the wells may not always be located one above the other. You may want to penetrate other wells laterally rather than vertically. And so under our circumstances, we wanted to reduce the half length if possible, possibly even creating penny-shaped fractures. So the 3 stimulations that were done on the injection well, and the injection well trajectory is shown here, an elevation view on the left and a map view or a plan view on the right. So the first stage was done in an open hole part of the hole. So below about 10,787 feet measured depth, there's an open hole that extends to just under 11,000 feet, 10,987 feet, say. And a slick water treatment was pumped, and this was tagged with a chemical tracer. Subsequent to that, a bridge plug was set to isolate that lower zone, and a cased and perforated zone was stimulated, once again using slick water. The casing was 7-inch, and bridge plugs were used to isolate zone 1. Slick water was pumped at a rate of about 35 barrels per minute, and once again, chemical tracer was injected. And finally, we moved uphole, set a bridge plug to isolate the lower 2 zones, perforated the casing, and pumped a cross-length carboxymethyl hydroxypropyl guar treatment, CMHPG, once again tagged with a distinct chemical tracer. Now, one of the things that you need to worry about in hydraulic fracturing of geothermal settings is that you have to carry proppant. And you probably have to prop these fractures substantially more than what we're used to in shale treatments. And so to do that, it's ideal to have a viscous fluid so that you can rely on a combination of viscosity and rate to carry the proppant and to avoid excessive proppant settling. So the third stage that was pumped in 2022 was a cross-length carboxymethyl hydroxypropyl guar. And this is just showing rheograms of pre-qualification testing of this guar. You can see a temperature profile that was adopted to try and simulate what is happening in situ. The temperature is shown on the right-hand vertical axis, and it's shown with a dashed red line. And so you can see the temperature was progressively increased to 350 and ultimately to 400 degrees Fahrenheit. And what we definitely see is that even with this fluid, that there's a substantial degradation in the apparent viscosity. So the right-hand side the left-hand side shows the apparent viscosity at 100 reciprocal seconds, which is somewhere in the range of what you might expect in a hydraulic fracturing, certainly away from the wellbore. And one can see that within 90 minutes, the viscosity is substantially reduced, and it continues to reduce thereafter. So this is one of the things that one has to deal with, and testing out the difference between slick water and a viscosified fluid was one of the challenges that was undertaken during this early 3-fracture program. Being uncertain whether or not we could run conventional frac plugs, bridge plugs were adopted, and these worked extremely well. They were provided by Interwell US, and all of the bridge plugs were successfully set and successfully retrieved. And this just sort of shows engineering drawings of running, setting, and recovery profiles for this particular bridge plug. So to put this into perspective at the forge site, here's an aerial view looking to the west, maybe a bit to the northwest, and it shows the profiles of the injection well and the production well. The injection well, in this case, shown in blue, and these fracs were done before the production well had even been drilled. What you can further see on this is that the fracturing stages, 3 fracturing stages, were done at the toe of the 16A well. And you can also see 3 monitoring wells. These were the 78B32 well, the 5832 well, and the 5632 well. And these wells were relatively deep. The 78B well was drilled to about 9,500 feet, actually. And so they're deep enough that you can emplace geophones in these wells. Maybe not to those total depths because of temperature restrictions, but deep enough to provide an effective realization of the fracture morphology from microseismic signals. So the first thing that was done in the open hole stage of this well was that a pseudo shear stimulation test was run. And basically this entailed bringing in low rate pumping equipment and circulating. And circulating, as you can see in the bottom right hand corner, the blue shows rate, and initially the rate was less than 1/4 barrel a minute, and subsequent to that the rate was increased to maybe 1/2 barrel a minute. And you can see the pressure response, and the pressure responded almost immediately, even at 1/4 barrel per minute, and it showed up opening up fractures and no strong indication of shear occurring. And basically once the fracture system was opened up, there was indication of propagation of fractures at stresses above the anticipated minimum principal stress. And the minimum principal stress had previously been determined by a DFIT when this well had been drilled. So subsequent to that low rate slick water it was actually casing. It was actually just water in the casing, displacing casing fluid at that time. But subsequent to that, stage 1 was pumped, and it was pumped in the open hole of the well by Liberty Oilfield Services, pumped down 7-inch, 38-pound per foot casing. And it pretty much stuck to an injection schedule of 50 barrels a minute, but seeing as this was one of the first times a granitic reservoir had been fracked, probably since Fenton Hill, or at least for geothermal purposes, that is, the rate was stepped up. And not only did that step up allow us to understand how easily the formation would break, but it also provided an indication of friction pressure, or a potential to evaluate friction pressure from the stepped injection profiles. And similarly, on shut-in, the step down allowed friction to be determined. So you can see in the treatment records, you can see the greenish yellow, which is the rate, and that goes to the right-hand side. So you see the rate was stepped up in 5 barrel per minute increments, and then held constant for what, maybe an hour, something like that, at 50 barrels a minute, and then stepped down. And you can see that the pressure walked up and stayed relatively constant. Initially, with some of the steps that were occurring, you can possibly see some incremental fracture growth that was happening, but everything pretty much leveled out, and it suggests possibly a balance between fluid loss with fractures in the open hole zone and the injected rate. The well was shut in for 4 hours, and then it was flowed back for 16 hours. And during that 16 hours, fluid was recovered, and the geochemistry was evaluated. Once again, just showing that the well was flowed back, and some photographs of the produced hot fluid during this flowback. Okay, so the first stage was done. It was flowed back for 16 hours, and then at that point it was time to set a bridge plug. The bridge plugs were adopted because we didn't know whether or not frac plugs were going to hold up to the temperature, and indeed we found later on, as you'll hear, that frac plugs will work just fine if you're pumping down the casing and cooling the casing adequately. But this entailed running bridge plugs, and you can see a bridge plug on the left. The element is shown here, and the bridge plug being run into the hole is shown in the two left-hand photographs. So subsequent to running the bridge plug, the hole was perforated. In this particular instance, we selected a portion of the wellbore that showed substantial FMI signatures where we thought that there would be ease in terms of generating a fracture. And indeed there was. Indeed there was. And so 20-foot guns were run just to make sure that we hit as much of this fracture as possible. And the perforations were 6 shot per foot at 60-degree phasing. So perforated, bridge plug isolating the lower zone, time to frack the well. And so Liberty pumped about just under 3,000 barrels of slick water down casing at a rate of 35 barrels per minute. And that rate was chosen because we just didn't know what sort of resistance there was going to be near wellbore and what sort of pressure we would have at the surface. Now, what you can see from the pressure records is that the red indicates surface pressure, the greenish yellow indicates rate, and rate is on the right-hand vertical axis. Pressure is on the left-hand vertical axis. You can see that partway through the job there was an intentional shut-in, and this was recommended by one of our advisors, Carl Montgomery from NSI, and the purpose of this was to do a cursory evaluation of the impact of cyclic injection on microseismicity. And this showed that the microseismicity did seem to go down a little bit after the shut-in. So one should keep in mind that cyclic injection may have a role in these geothermal stimulations. However, you also have to keep in mind that we found from all of our fracturing activities that almost certainly do you have to pump proppant. And having periodic shut-ins while pumping proppant complicates treatment schedule substantially. So nevertheless, this treatment went away smoothly. You can see that once again the rate was stepped up in 5 barrel per minute increments and stepped down in 5 barrels per minute increments. You can also see that no proppant was run. In any of these 3 stages, no proppant was run. And the reason for that is that we were uncertain how these wells were going to treat, and we were committed to avoiding screenouts in these treatments. So the well was shut in. It was held shut in for 4 hours, and it was flowed back for 12 hours. It was flowed back enough so that the rig on location could start to run the next bridge plug into the hole. And so that bridge plug was run into the hole and set above the stage 2 perforations so that stage 2 could go ahead. Stage 3 could go ahead. Perforations were shot. guns were pulled, and once again Liberty pumped at 35 barrels a minute. In this case, they pumped a different fluid. They pumped cross-linked carboxymethyl hydroxypropyl guar, and a little bit of deep prop micropropant was pumped at concentrations between 1/2 and 3/4 of a pound of propant added. About 3,000 barrels, so pretty much the same size as the previous stages, but a different fluid. The well was shut in and it was flowed back for more than 15 hours. This is the treatment record for that particular stage, and you can see that this treatment record tends to suggest vertical height growth or significant radial height growth without a substantial amount of fluid loss. Possibly some fluid loss. It's difficult to say. Of course, this is not a Nolte-Smith plot. It's just a plot of pressure. The red curve, the left-hand vertical axis, and rate, the yellowish green, the greenish yellow curve, vertical right-hand axis, and the deep prop at the surface and when it reached the perforations. And you can really see no substantial signature of the propant reaching the perforations. At right is a microseismic composite map, courtesy of Geoenergy Suisse, that is showing, a pseudo-radial fracture if you look at it from this angle, that extended maybe 400 feet vertically. And that enabled us to site the production well with some level of confidence. And as I mentioned, an important part of all of these measurements has been the seismic monitoring. It turns out that in this particular well, there were geophones, multi-chain geophones in 3 wells, and you can see the depths of the geophones in those wells. There were 3 wells with geophones, but not all of them worked all of the time. In fact, for stage 1, only 1 set of geophones worked. For stage 2, 2 geophones were functional, and for stage 3, all 3 geophones were functional. And as you can see from this microseismic compilation, some tremendous information was derived from the geophones. To put this into perspective, the blue well is the injector, the magenta well is the anticipated location of the production well, and the grayish white sleeve at the tip of the blue well is the open hole zone where stage 1 was carried out. And you can see that stage 1 was relatively aseismic. Stage 2 is somewhat diffuse. It was slick water, but it cannot be confirmed that slick water alone was the cause of this diffuse characteristic of the mapped fracture. The reason being is that only 2 of the geophone wells were functional for this stage. Whereas if we move uphole to the upper left, we have stage 3, which is a very, very classic representation of a pseudoplanar fracture, possibly with some bifurcations associated with natural fractures, but relatively planar. And if we looked at this in gun barrel view, you could see that it's actually relatively radial in nature. If we look at a recap of the 2022 stimulation effort, we can see that there was a strong performance by the bridge plugs. They sealed effectively, they handled the temperatures, they handled the pressures, and they worked very effectively. However, in the long run, one needs to carry out these operations rigless, and wireline deployable devices are needed, and drillable isolation tools are required, or dissolvable plugs, in fact, would be desirable. And I think that the industry has moved in this direction. Coiled tubing could be considered for drilling out plugs. And we did experience some difficulties in pumping low concentrations of microproppant. We also determined that ruggedized geophone packages that could tolerate temperatures above 150 degrees C for protracted periods of time were desirable. One of the more interesting elements of stage 1 that I didn't really mention was that it was relatively aseismic up until a certain point, where you started to see signals developing substantially away from the wellbore and actually moving back to the wellbore at an angle. And that angle suggests that there were viscous losses in some sort of natural fracture. We did indeed find from this that cased and perforated completions were an effective methodology, and we demonstrated the potential for use for viscosified fluids. There's a possibility identified by the hard shutdown during stage 2 that there may be some benefits from cyclic stimulation. And finally, we certainly confirmed that proppant was desirable in these fracture systems. The next question you ask is, how does one go about validating or assessing the degree of connectivity between these wells? Well, we did this by carrying out some short-term circulation tests, and here is a timeline that reflects that testing. So, as you recall, we finished drilling and completing the injection well in January of 2021. In April of 2022, the 3-stage stimulation testing that I just discussed was carried out. And once that was done, the production well was drilled to intersect the microseismic clouds that were identified from the stimulations that were carried out in June 2023. Subsequent to that, 2 circulation tests were carried out in July of 2023 at rates up to 7.5 barrels per minute. The first circulation test was carried out in July 4th and 5th, 2023, where fluid was injected down the 16A well, and you can refer to the left-hand panel. And that fluid was injected, it passed through the fracture system, and it had the potential to be captured by an uncompleted section of the 16B well. This was before the production casing had been run, so essentially open hole along its entire length. At the right is a panel, shows a test that was done 2 weeks later, after casing had been run and cemented in place. And you can see a cartoon illustrating where the casing could be and fracture morphology if planar vertical fractures had been created. So what really happened? What sort of connectivity was there? Well, these 2 diagrams indicate the degree of connectivity, and their measurements from the second of the circulation tests, July 18th and 19th and 20th of 2023. Basically, left-hand panel is July 18th, right-hand panel is July 19th and 20th. And they show in blue the injection pressure on the injection well, quite high, okay, indicating the substantial amount of impedance to flow between the wells. And you can see the red curve, which indicates the injection rate, and that injection rate is shown on the right-hand vertical margin, reaching approximately 7.5 barrels per minute. You can also see gray dots, which you say, well, fantastic, it's showing communication. Indeed, that's true, but notice the scale, that the scale of the injection was in barrels per minute, and the scale of the produced fluid is in barrels per hour. So producing 16 barrels per hour and injecting at 10 barrels per minute. So really a poor connection illustrated in both of these panels. And what is the reason for that? Well, there could be a number of reasons, and I mean, there's no viable proof of any of them, but it suggests that proppant may be required. That seems like a number one situation, that the fracture had closed down and that propped fractures were required. And number two, it may be necessary to enhance the connection at the production well by physically fracturing the production well. And I think we've established at the forage site that probably both of those are true, at least in the case of forage. In addition, on the circulation test, after the second set of testing, a production logging tool was run. And this production logging tool involves running pressure, temperature, and spinner measurements. And the spinner measurements are shown here for stages 1, 2, and 3. Recall, stage 1 was open hole, slick water. Stage 2 was cased hole, slick water, and case 3 was cased hole, cross-linked fluid. And it's showing a preponderance of flow into the lower zone, the open hole zone, which is interesting. That has not been duplicated in subsequent tests. And a preponderance of the remainder of the flow going into the fracture that was pumped with viscosified fluids. So things to just bear in mind. Well, so this was done, and some months later, a field large-scale fracturing test was done. This overview is a view to the east, showing in the mid-distance, mid-background, it's showing two frac tanks holding fluid from a well on that pad. It's showing in the foreground 2 ponds that were used to accumulate that fluid, as well as Calfrac frac fleet. You can see the injection well 16A with a workover rig on the right, and 16B with a workover rig on the left. And injection is, in this particular case, going into 16A at this time. Here's another view of that. You can see the 16A pad in the distance as looking west. You can also see the trajectories of those 2 wells and the monitoring wells, 5832, 78B32, and 5632, that all had geophones in them, along with surface nodal networks of geophones and some permanent geophones in shallow well 6832. One of the things that really enhanced monitoring was the installation of fiber optics in the production well. The fiber optics was cemented between the casing and the formation, and was a tremendous success, a tremendous benefit in terms of scientific information from these fractures. Installation turns out to be absolutely critical, and we were lucky enough to have very good partners in this. One fiber optic string was run by the University of Texas in Shell, shown at the left, and this was a flat pack. And Rice University and Silixa ran a more conventional capillary tubing with the FIMP inside. Baker Hughes ran a fiber-connected pressure temperature gauge, and this penetrated the casing at a location near the heel, and so provided downhole pressure and temperature information. As I mentioned, the installation was critical, and we relied on designs that had been devised by our partners and used successfully at other locations. And this involved completion cable protectors, and these protectors are shown in this pictures. They're quite complicated, and while it takes some time to install them, they're very effective in protecting the fiber. This is a montage of some of the fiber installation operations. At the far left, you can see 3 shivs, one for each cable. And moving inwards, you can see Baker Hughes technicians installing the cable protectors. The yellow reel is the shell flat pack being unreeled, and the Solixa capillary tubing is shown going up to the shivs on the photograph second from the right. The photograph at the far right shows fiber optics, one of the fiber optic cables, one of the 3, coming out of a hanger in the wellhead. So let's talk about the chronology of the stimulation activities that these fiber optics monitored so well. 8 stages were pumped on the injection well, and 4 stages were pumped on the production well. In all cases, there were geophones installed in the 3 wells that I mentioned, and we adhered strictly to a traffic light system. We never had to move from green to amber, but it's essential for these criteria to be in place. Well, this is a drone view of the CalFrac fleet showing the rig sump. You can see both of the workover rigs over the wells, and you can see CalFrac's frac fleet in place, along with 2 harpoon tanks containing water that was used in the frac work. In addition to the fiber optics, we also injected distinct tracers in each stage, and these tracers included Quantum Pro's nanoparticulate tracers and Resman's chemical tracers. And this is a subject for another webinar, but extremely valuable information delineating the residence time in the formation and the characteristic frac paths that the fluids are following. So let's just look at some characteristic stimulations. So what does stage 3R? Well, the R stands for refrac. So the first stage that was pumped in well 16A was a refrac of stages 1, 2, and 3 that had been pumped in 2022. And so as you recall, those were an open hole and 2 20-foot long clusters. And the restimulation was done with about 10,000 barrels of clean fluid pumped at an average rate of 50 barrels a minute. And it was slick water. And in these cases, sand was pumped as the proppant, 100 mesh sand followed by 40/70. And so the diagram of the treatment records on the right shows the data. The black curve, let's not pay attention to it, but it is a first order prediction of the bottom hole pressure. It's been adjusted subsequently to more accurately reflect friction, but it's going to include hydrostatic pressure. The red curve is the surface treating pressure measuring at the surface. And pressures are recorded on the left-hand vertical axis. Rate and proppant concentration is shown on the right-hand vertical axis, the blue curve being rate. So you can see 50 barrels a minute was pumped after it reached rate, and the proppant concentrations at the surface and at the perforations are shown also on the right-hand vertical axis. This job basically was pumped as planned. You can see that towards the end of the job, just before we went on flush, there was a slight trend for an increase in pressure, and the substantial increase in pressure was because of the flush fluid. So this job went as planned. You can see some sort of likely radial frac growth, and then ultimately stable growth followed by following that. and it was basically pumped as planned, and the pressure starts to build just before the 1.25 pound proppant added 40/70 stage. In all cases, we had frac hits measured, and you can see these frac hits measured with the fiber optics. This is a typical waterfall plot showing depth, measured depth on the vertical axis, and time on the horizontal axis. And you can see about 4 intersection points were picked on the production well. So 4 frac hits at discrete locations on the production well is delineated by fiber optics. So stage 3R was pumped successfully. Then stage 4 was pumped. That was a slick water treatment, single cluster, and at a rate duplicating what was pumped previously. Stage 3, duplicating stage 3. Stage 5 was a slick water, was a cross-link fluid treatment, and then we went to, and that went away fine. And then we went to stage 6. Stage 6 was a slick water treatment, single cluster, and well, you can look at the treatment record and you say, well, that looks a little different. So what that treatment record shows is that with a wellhead pressure limit set at 8,000 psi, we were walking up to that wellhead pressure limit and we were not fracturing. And eventually we started to get fluid into the formation, and so we got the formation taking fluid. But after 6 hours, the rate was low enough that we were not confident that pumping proppant could be achieved without a screen out. And so we went on to stage 6B, an unplanned stage for this, an unplanned part of this stage. So what did we do? Well, we added another set of perforations. We looked at the FMI log, and there was an area that had been high graded for potential natural fractures, and we perforated in that zone. So we added another cluster, and we went back in and we started pumping again. And the same sort of issue occurred, that we could put fluid away, and we tried high viscosity HVFR, cycling, hard shutdowns, and whatever, but we just did not reach rates where we felt comfortable to pump 100 mesh sand, let alone 40/70 sand, for risk of screen out. And so another gun run in an alleged naturally fractured zone, but didn't make much of a difference, and we were treating at our maximum allowable surface pressure. So why did this happen? We went back and looked at the logs, and we had a spectral gamma log from this particular well. And if you start to look at it, and you look at the gamma ray, you can look at the depth of stages 6 and 7. You can say, well, maybe there's a hump in the gamma ray there, suggesting some sort of difference in lithology. Maybe the potassium, well, it looks like the potassium is going down. The thorium's going up, uranium might be going up. So is there something different about this zone? And it's not obvious from this, and it's not obvious necessarily from Young's modulus determined from the sonic, but probably you are dealing with a different zone, a different lithologic zone. And this is an important message for these granitic reservoirs, that one says, well, they're homogeneous, but really they're not. There's different genres of granitoid and different lithologic characteristics, and they all can apparently treat differently. And this is something that reservoir characterization in advance might be relevant, although it was pretty hard to spot this on the gamma ray log. Nevertheless, stages 6 and 7 identified a different geologic regime. Stage 8, well, stage 8 had been planned to increase the number of stages so that we could test out what 8 perforation clusters would look like, pumped with a cross-link fluid. And indeed, stage 8 was pumped uneventfully, unlike the two previous stages before. It was pumped uneventfully. These clusters were 8 clusters, 25 feet apart, and a large volume of fluid was pumped. 35,000 barrels of fluid, 1,000,000 pounds of sand at 80 barrels a minute. And this treatment went away very, very classically. You can see a rise in pressure. The first part due to seating the ball in the frac plug, and then subsequent to that, pressure rise associated with pressuring up and ultimately breaking over gently, and then building up a little bit with propagation, probably some sort of lateral growth, and then a little bit more radial growth and probably some fluid loss occurring, but it treated very, very easily and normally. However, and this was a crosslink fluid. However, stage 9 was a little bit different. The nominal stage design was identical to stage 8. Eight clusters, 4-foot guns, 6 shots per foot, 60-degree phasing, and but the difference being slick water was pumped rather than crosslink fluids. And as you look at the red line, which is the pressure, you can see that it was a little bit more challenging. That the pressure increased, then it went down, and then towards the end of the treatment, you really started to see indications that screen out was something that would happen relatively soon. So we went to flush before the entire job was pumped. And so the question is, what's the difference between stage 8 and stage 9? Well, one obvious difference is stage 8 was cross-linked fluid that may not have penetrated natural fractures as easily. Stage 9 was slick water, where viscous losses into natural fractures might have been more convenient. And one more stage was pumped. That was stage 10, and that used an experimental ultra lightweight fluid. As I've emphasized, the fiber optics, as shown in this waterfall plot, were absolutely essential for understanding what's going on in this reservoir. And you can see that something is in particularly odd is starting to happen with stage 8, possibly even with stage 7, but 8, 9, and 10 are all amalgamating to being produced at a very similar location. And there'll be more, and in a few minutes, there'll be more on that. The microseismic data is absolutely stunning. You can see the long fractures associated with the large volumes for stage 8 and stage 9, and smaller fractures created for the other stages. So we fracked the injection well, 8 stages, including a refrac. And while we were fracking that injection well, we were taking frac hits at the production well, as indicated by the fiber. Now, I'll elaborate a little bit here in terms of the fiber. The fiber was behind casing in 16B, cemented in place, and to be able to perforate this well, you have to be able to locate the fiber. This well had an experimental bridge plug at its toe, and that experimental bridge plug prevented circulation for cool down. We were able to have circulation for cool down in 16A, so we could use conventional frac plugs and run them on wireline, and that worked very well. Whereas on this well, with that bridge plug in place, we couldn't cool down the well, so we had to run frac plugs on drill pipe, and it was much more difficult, and there were failures because of temperature. It was a custom designed bridge plug that had basically met temperature requirements, but there were a number of premature sets and difficulties in terms of this. And so when you're running this, you recall that you are perforating. We were running perforating guns on pipe, 0-degree phasing, and used Halliburton's G-force system for the perforations to be rotated and oriented in a direction away from where the fibers had been located. And the fibers were located using a combination of USIT and magnetic flux methods. It worked reasonably well, but there was some serendipity involved, I believe, in terms of nothing was penetrated. Now, so we located where the frac hits were, and now we're ready to perforate that well with the guns, now that we know where the fiber is. And we perforated using high explosive charges, HNS charges, and we perforated where the frac hits occurred. So we looked at the frac hits, grouped them into reasonable frac stages, and went about perforating and fracking sequential stages. And here's an example in stage 1. Okay, you can see that it's got 4 clusters, pumped relatively small treatment, about 4,500 barrels of neat fluid, of clean. There was 4,500 barrels of clean fluid that was pumped, but in addition to that, there's about 100,000 pounds of sand that went with that at an average rate of 60 barrels a minute. Now, the interesting thing in all of these is, notice at about 11 minutes, and you can look at the red curve, the pressure signature. Notice the sudden drop in pressure, and the sudden drop in pressure, and then a recovery. And it's as if the fracture that you've created from the production well has met its mate from the injection well, or met a mate from the injection well. And of all the 4 zones that were fractured, this occurred in each one of those zones. That there was a pressure drop and a recovery. And as I mentioned, just enormous value from the fiber optics in the production well, and this is just one example. There are a number of reports on the geothermal data repository that document the fiber optics findings from these stimulations. So you've carried out these stimulations. Well, how effective were they? Well, the best way to find out is to circulate between the wells and see what sort of connectivity you have, and how much fluid is going from one well to another, and how well does the temperature hold up. That's the ultimate goal of these types of experiments. So here are the results from a 30-day circulation test after this fracturing campaign. The right-hand vertical axis is the blue injection rate. You can see that it's pretty constant at 10 barrels a minute. And the red curve corresponding to the vertical axis on the left is the injection pressure. The thing to notice about this is that the injection pressure, well, it's going down a little bit, but it's still pretty high. It's like, 2,800, 2,700 psi, and you're pumping at 10 barrels a minute. If you work that out, that's a significant amount of power, and that power has to be taken off the net power of any sort of energy that you would reduce. And so this is an important consideration, is what sort of methodology is there to reduce the impedance to flow from one well to another. We pretty much know what the friction losses are in the pipe. We're uncertain about what the near wellbore losses are, or even what the morphology of the fractures are, but maybe a lot of this is related to the low proppant concentrations that are in the fractures interconnecting the wells. And I think that's an important point. We'll come back to it. So pressure's high, but temperature was high too. The temperature is the lower curve corresponding to the right-hand vertical axis, and temperature was relatively constant and stable, and which was a good sign. Okay, the bottom hole temperature is about 420 Fahrenheit, and we were measuring 375 to 383, depending on what measurement system we used. The more interesting curve is the blue curve, which we'll call the efficiency. And the efficiency is the ratio of the produced mass flow rate to the injected mass flow rate. And you can see it's heading towards 90%. And while that's good, it's something that needs to be improved when you think that that 10% of lost fluid has to be made up with well water or whatever your water is. And over a 30-year period, if that doesn't stabilize and max out at a higher level, then you're going to be experience a significant expense and possibly hazards associated with a substantial amount of lost water. So maybe the number one thing, one of the three number one issues to sort out with future work at Forge. So remember this efficiency. This is something that we shouldn't forget. In addition, we made efforts using production logging tools or pressure temperature spinner surveys to delineate where the fluid was exiting the production well. Well, actually, this is showing where fluid is entering the injection well. And I'm even going to step back a year previously. Immediately after the fractures were done in 2024, there was a 9-day circulation test after the production well was fracked, and it looks at where fluid is going into the well. We were only able to get the tool down to above where stage 6 was pumped in the injection well. And so you can see stages 1 to 6 are lumped together, and about 34% of the fluid coming out, going into the hole. Stage 7 doesn't show anything or shows very, very little contribution. Stage 6 shows nothing. Remember, those were two zones that were not propped. Stage 8, it's showing 15% of the flow. Stage 9 is probably showing a little more than 15% of the flow, but what you see in stage 9 is that not all of the perforations were contributing equally. We have a similar plot of the perforations in stage 8 that I'm not showing here, but it carries a similar message, and that message is demonstrated in the following slides as well. These following slides were taken in August 2024, after the 30-day circulation test, and in August 2025 after a 7-day circulation test carried out by Texas Tech University. And what we see, well, let's look at the left-hand panel. What we see is in August 2024, we still had a fair bit of fluid coming from the bottom of the well. We couldn't get all the way down, so some of that's lumped. Stages 4, 3, 2, and 1 are all lumped together. But notice there's no fluid at all from stage 6, no fluid at all from stage 7, unpropped fractures. Stage 8 shows fluid coming in, but only about a 50% uniformity. Well, only about 50% of the clusters are producing substantially, and the same thing with stage 9. Then we go a year forward, and we see something similar up above, except now we are not seeing a substantial amount of fluid coming from down below. From the bottom, and it's like a heelward bias is really starting to dominate, and so this just illustrates the importance of conformance control, inflow control devices for future activities to control where fluid is entering these wells. Now we're going to sort of finish off, or come close to finishing off, with one of the more interesting findings from all of this, and it's based on the frac hits that were determined. So let's look at this cartoon. This cartoon shows the injection well at the bottom, the production well 300 feet above it. On the injection well, we see a different color for each frac stage, and each circle represents a cluster. So stage 3 had 1 cluster, stage 7 had 3 clusters, stage 8 had 8 clusters, stage 9 had 8, etc., etc. And so that's where fluid was nominally exiting the well during fracturing. On the production well on the other side, we're showing colors that correspond to the individual stages, but those are frac hits. Those are where dominant frac hits occurred. And we want to look at where those frac hits occurred because it's an important message. And we'll do that by just sort of blowing things up a little bit. Okay, let's look at stage 3. Okay, so we're pumping stage 3. We can say single cluster in stage 3. It reaches the production well at 4 distinct zones. So single fracture branches into 4 zones, or at least connects in 4 different spots. Okay, that's fine. How about stage 4? Well, we pumped stage 4. It came out in the same 4 spots. How about stage 5? It came out in the same 4 spots. So somehow there's a corridor of fluid that is shared between stages 4, 3, and 5. And that one of the potential reasons for that is natural fracturing causing this intermingling and creation of a cluster. Stage 6 stood on its own, wasn't vertical, but it was discrete. Stage 7 stood on its own, wasn't vertical, and it dips in the other direction. So it's kind of interesting that there's some sort of change in the stress field or whatever is controlling the fracture propagation. Stage 8 is of particular interest. Look at the 8 clusters 25 feet apart on the injection well. And then there's more than 8 frac hits, and the frac hits are spread out over about 500 feet. 200 feet in the injection well, 500 feet in the production well. Seriously suggests some sort of geologic intervention and fracturing. And one of the more interesting things is that the uphole hits occurred first, and that you could see fracture hits growing downwards, whereas you would normally think it would be the other way around. Now here's stage 9 slick water, and let's see if I can go back. Maybe not. Stage 9 and stage 10. Stage 9 and stage 10 both exit at the same place as hits at from the end of stage 8. And so we've got a corridor for stages 3, 4, and 5, and we've got a corridor for stages 8, 9, and 10, where stage 8 is really an anomaly, and stages 9 and 10 are exiting the wellbore at the same place as much the flow from stage 8. And that's reflected in some of the heelward bias that we see on the production logging tools. So that's an important conclusion. And let's just sort of back up and look at some of the critical questions that we've seen and are not yet resolved for circulation. We have not seen thermal breakthrough. That's why we plan to carry out a 4 to 6 month circulation test starting starting shortly. We are uncertain what the best layout of wells are. We had a production well immediately above an injection well, counting on buoyancy. That may not be the best layout for thermal sweep. You may be looking at a wine rack, you may be looking at other configurations. We found that geochemistry, and I haven't had time to talk about it, I'm sure there'll be a webinar on that. The geochemistry is absolutely essential, and we ran corrosion and calcite inhibition, carbonate inhibition during our 30-day injection test. Conformance, the regularity of flow between through individual perforations, absolutely essential. And it's complicated by interactions with natural fractures, at least that's the predominant theory at the present time. And one needs to decide, do you avoid issues like this if there's natural features? Can you resolve them? Can you mitigate them? Really an important consideration. Inflow control devices are going to be essential. Then the other thing to remember is that efficiency. We had 90% efficiency, 10% losses, and so we want to improve on that. We want to see during this longer-term circulation test whether the system tightens up and less water is lost, and whether or not the parasitic load reduces. All sorts of technical issues that one can consider in hydraulic fracturing. Mechanics of isolation. Do we continue with cased and perforated? We can certainly use conventional oil field technology. or is it necessary from the perspective of inflow control to move to sliding sleeves? Proppant. Is silica proppant adequate? On its own, in a non-equilibrated, undersaturated system, silica will dissolve substantially at 200 degrees C. Do we need to move to ceramics? Or will this be mitigated if the system is a continuous circulation of equilibrated fluid? It's yet to be determined, but I think we are, at least for the time being, moving towards thinking about ceramic proppants. An extremely important point, and that we probably have inadequate fracture conductivity. Recall once again, and I'll repeat this, that in shales, the controlling factor is the permeability of the shale itself. And the conductivity of the fracture is almost inconsequential because it's so much larger. And with that in place, and based on using slick water, you can rely on small concentrations of small diameter proppant to have adequate oil or gas production. That is not the case in enhanced geothermal. You need highly conductive channels between these fractures, and so I think there needs to be a move towards pumping larger proppant at higher concentrations. And of course, to do that, you're going to need fracturing fluids that can tolerate the temperature. And that will be, I think, another source of innovation and research and reinvention within the fracturing industry. And we've talked about natural fractures previously. So to reiterate on circulation issues: water losses, parasitic loading, conformance control, geochemistry. Those are the challenges of the future, and those are the things that we'll try and address in upcoming field work at Forge. A 4 to 6 month circulation test looking for temperature decay or temperature stability, looking for changes in water loss, looking for changes in parasitic load, and looking for what sort of conformance we have with a longer term. And finally, we would like to thank the Department of Energy for sponsoring the Forge endeavor. It's made a real impact on comprehension of enhanced geothermal systems.